right, so we're back to talk about how to code Newton's method for multivariate functions. So I've already written the code to solve the example in two different ways, but I thought we could go through it and I could talk about each line and then comment it. We can comment it together as we go through instead of actually coding it together. Okay, so hopefully you can see this. I'm just going to start with a code that looks basically exactly like the code from lecture 14 with a scalar valued function. I'm going to choose some number of steps for iteration. I guess it's the number of steps. So that's n, and I'm going to initialize a vector x, sorry, not a vector, a matrix to save x's. So now in this case, we have x1 and x2. So I'm going to save this as a column vector for each time step. So it's going to be a 2 by n matrix. And I'm going to populate the first column of that matrix, so x colon 1 comma, colon comma 1 in line 5 with my initial condition. So we noticed that there looks like there is a root or an intersection of these two functions near -3, 0. So I'm going to use that as my initial condition. Now I'm going to run a for loop for the next n steps. Oh, whoops, I guess I need to make x n plus 1 long. So run a for loop for n steps. And in that for loop, I'm going to run the Newton's algorithm. So Newton's method. So for the case of a multivariate function, x at k plus 1 is equal to x at k minus the Jacobian inverse. So here I have the Jacobian. We'll talk about what that function is. It's my Jacobian. So the output of that function is a matrix, and so it's to the -1, and then times my function. So let's go down to the functions here below. So for my function, now we have a vector valued function. So you put it in like a vector. I have two inputs, x1 and x2. Of course, I'll upload these codes onto Canvas as well. So I do element-wise multiplication. I'm not quite sure if I need element-wise multiplication here because these are just scalars, but in any case, I put in element-wise here just to be sure if I put in, like I wanted to plot a vector of functional values, that would work. And so I put in the functions as we have them, x1 squared plus x1 times x2 cubed minus 9, and then just to not have them all in the same line, I put a semicolon so it goes down to the next element of the vector and a dot, dot, dot. It's easier to read. And then 3 times x2 times x1 squared minus x2 cubed minus 4. So that's my function. I put my Jacobian as a matrix just in the same way. So this is the analytical Jacobian that we found on page 8 of the notes. And you can see the elements here. Again, the inputs are x1 and x2. So I'll say input scalar x1, x2, oops, and the output vector of the functional values, f1 and f2. f1, f2. So for my Jacobian, I'm going to input x1 and x2, and I output matrix, a Jacobian matrix. So 2 by 2 Jacobian. Great. So I run through the code. I do it n times, so n is 6. And then I end up with this matrix of x values. I want to look at what the final value is. That should be the approximation for the root. And then I want to check how good the approximation is. So I'm going to look at the functional value of the last element. Remember, I'm going to input the inputs of my function should be a scalar. So I have to take the components of x, so x1 and x2, the components of that column, the last column of the matrix separately. And I get this column vector, and then I'm going to take the norm to make sure it's a small number. And then here I have a plot where I'm plotting the elements of the vector. So let's take a look. I'm going to share the plot with you. It looks like it converges fairly quickly. So the elements of the vector, we can't tell the order from here, but I also made in the title the actual fixed point, or sorry, the actual root of the function. So -3 and 0, and this one is really close to -3 where it started, and this one is 0.14. So it goes up a little from 0 and then converges really quickly. This is how I find the roots. If I want to look at the other roots, I know there looks like there's one near 3, 0. And let me share the output screen with you. Here you go. So that one converged to something around 3, 0, and the other two look like they're at something like 1, 2, and -1, 2. So here's the thing. This is definitely one way that you can absolutely write the code. But I thought I would take this opportunity to tell you about how you could do this in a for loop in kind of like a nicer and more compact way to find all 4 roots at once. So what I just showed you is lecture 15 example 1.m. Here's lecture 15 example 2.m. So here's, again, I've written the function already. We can go through and comment it. So here's how the function goes. Then below, below starting line 16, I have a plot, which we'll talk about. And then below line 27, I have the 2 functions for my function and my Jacobian. Those are the same as in the last code. Same example. I just want to find all the roots at the same time. So here's how I'm going to do it. I'm going to input this IC vector. I guess it's not really it's a vector of 2-dimensional ICs, so it's a matrix. So these are the all the 2D initial conditions I want to try. I'm putting in the command window here. So I have 3, 0, -3, 0, 1, 2, and -1, -2. From the plot, it looks like this is close to where we need to go. So the outer loop here is a for loop with the index I, and that's going to go through these 4 different initial conditions. And where I'm going to save the data, and so maybe I'll write up here, these are initial conditions to test. And this is a for loop over the number 4 initial conditions. Great. And again, what I want to do here is I want to go through all 4 of them, but I don't know how long it's going to take for each of these to converge. So I wanted to use a while loop rather than a for loop, just as you did in lecture 14. So I thought this was a nice opportunity to show you how to use something called a cell array in MATLAB. So in MATLAB, we have matrix, like numerical arrays, and they can have as many dimensions as you want, but they have to be consistent in their size. So if I think of like a 3D array, or even a 2D array, like a matrix, I can't have one column have a different number of entries than another, right? I can't have like column 1 is 2 elements and column 2 is 5 elements. MATLAB would not like that. So what you can do is use something called a cell array, which is an array, if you think of it like pages in a book. So what is on each page can be a different type of data. One could have strings, one could have numbers. Not only that, it can be different sized matrices. So what I'm going to do is for each of these ICs, I'm going to have a different sized matrix of x's. So the x like we had before, where each x is a matrix that is 2 by some n, and each column is going to encode the convergence of Newton's method towards the root. I don't know how big it's going to be, so I'm just going to keep building it as I see it. The way that I denote a cell array is with these curly braces. So if I said y with curly braces 1 is 3, you can see here the command window. So there's what MATLAB just heard from me is I have a cell array, It's named Y, and it's the first page in that book is just the number 3. And maybe the second page in that book, so Y curly braces 2, is some 4x4 random matrix. So now when I ask it to print Y, it says, oh, it's a cell array. First I have just the number 3, and then I have a 4x4 double precision number matrix. So I can't even read what those are. So this is 3, and this is some matrix. Great. So what I'm going to do is use the concept of a cell array to build up these x's where I save the convergence of my Newton's method. So x, the ith cell of x. So when I start with I is equal to 1, like the first cell for the first root, I'm going to set the initial condition as the first column of IC vec. And then when I do I is equal to 2, I'm going to say, okay, now I have the second page in my book, the second cell, and that's going to use the second column of the IC vec for the second IC. After that, this becomes really the same, really similar to the algorithm that we did in lecture 14. So K is going to be a counter that it's going to start at 1, and then I'm going to have a while loop. We'll talk about the condition on the while loop in a second. And inside the while loop, I'm just going to run Newton's method. Run Newton's for multivariate. The only difference is now x always has to be xii in all of these arguments because I want to know which page of the book I'm on. So I run Newton's and then I update my counter. Update counter. So what is the condition on my while loop? The condition is that I want the absolute value of the norm, the function that was the last time, of the functional value of xk, now on the ith page of the book, to be greater than 10 to the negative 10. If it's less than negative 10 to the 10, then I get kicked out of the loop. I've converged, and I was printing the norm to see that it was small enough and the root just for myself, but we don't need to even print those. I just wanted to see what that was. We'll say print for debugging. And I guess let's come up with a comment for this while loop. We'll say this is run a while loop for the algorithm as long as the norm of x sub k plus 1 is greater than 10 to the negative 10. Hopefully that's clear. Okay, so I'm going to run that, and I run it, and it runs fine. And then I'm going to get some plots to look at the results. So the plots I'm going to look at are just the first page of the book, x with the curly braces 1, the second page of the book, the third, and the fourth. I'm going to look at them each as subplots. I think we've talked about subplots before, but I'll say I have a 4x1 matrix of plots, and I'll have the first plot, the second plot, the third, and the fourth, where I'm just going to plot the points so over the time step, so I can watch it converge. And then in the title, I'm actually going to write what the root is. So let me show you what that plot looks like when it generates. So here it is. So I have 4 plots. I have 4 roots. The top one is inexplicably blue. And here we see the one that starts at 3, 0, really close to 3, 0, the minus 3, 0, 1. That was the one we looked at before. We have the one that we started out by 1, 2, and it converges to 0.13, 0.17. And the one that started out by minus 1, minus 2 converges to this vector here. And so that's how I could use a cell array to compute an arbitrary number of roots all at the same time with an arbitrary tolerance for accuracy. And so that's it. All right, that's the end of lecture 15.